Both Unit 11 and Subtopic 11.1 have the title of Electromagnetic Induction. In order to make sense of electromagnetic induction, we actually need to refer back to Subtopic 5.4. Subtopic 5.4 is the magnetic effects of electric currents, and in that we saw that moving charges experience a force when they're in a magnetic field. So, statement here, we saw that a charge moving through a magnetic field experiences a force. And in order to explain this idea of electromagnetic induction, we'll just very briefly talk about that force again, and then take it a step further. The force that we're dealing with, if we look at a magnetic field as represented by these crosses, so that's showing that the field's going into the screen, and that's the magnetic field B. If we have a charge that's positioned here, we'll deal with a positive charge, moving in that direction with a velocity v, then as that charge moves through that field, it's going to experience a force that initially will be directed up, so the right hand palm rule can be used there, so fingers directed into the page or into the screen, thumb pointing to the right, so your palm will be pointing up the screen. That means that this charge will then experience a force that causes it to move in a circular path. That's because as the charge changes direction, the force will also change direction, so it will always point towards the center of motion, concept covered in Unit 6. So that's what happens with a charge, but if instead of just dealing with a single charge, let's imagine that instead we're going to have a conductor. So by a conductor I mean just a metal rod of some description. And in that metal rod we're going to have charges that are constrained. So they can't move anywhere, they can only move along the rod itself. So when charges are constrained, what we're going to see is movement of those charges along the conductor. As the conductor moves through. So as it moves through the magnetic field, the charges, or the positive charges, are still going to experience that force that pushes them up. And so they'll move one way. So up in this particular scenario, and negative charges will move the other way. So realistically what we're talking about there is not so much that you've got both positive and negative charges moving. It's realistically we're just dealing with electrons that would be moving, but we can consider the separation of those charges as though it is that the positive charges are moving. So again, as this conductor is now moving through that field with a velocity, what we're going to see is that as the conductor is moving, positive charges are going to experience a force that pushes them up that way, and negative charges will be pushed down the way. So what we end up with, keeping in mind that this is a case of motion, we're going to have these positive charges that get pushed up to the top and negative charges that get pushed down to the bottom. Now the really important thing to note here is that we now have a separation of charge. So the separation of charge here is the important thing, and this is where the electromagnetic induction comes in. So the separation of charges in that conductor, or between the ends of the conductor, establishes a potential difference. So we have a potential difference between the two ends of the conductor, and we'll talk a little bit about what that potential difference is. So that's great that we've got a potential difference there, but what can we do with it? Well, if that conductor is now connected to something else, and that's something else that we'll talk about here, the easiest thing to identify here is a resistor. So if the conductor is connected to a resistor, that then means that current can flow through. So those charges no longer will be separated. They'll be able to flow through the conductor itself, through the resistor, sorry. So the way to think about that in this scenario is to think about a conducting rail. So in this case you might have, so out to the side here you have a metal rail that is stationary, so having a resistor positioned here, and the conductor can then slide along that rail. So the conductor is still moving to the right. That will then establish a current through that resistor. So a current can now flow that way because all of these negative charges, positive charges, can now move through the conductor itself, and therefore through the resistor. Now the thing that we're most interested here though is the potential difference. That potential difference has a particular name. So the potential difference here, it's a bit of a confusing name. So think of this as being more a description of what this potential difference does, rather than a description of the quantity itself. That potential difference is known as an electromotive force. That usually gets abbreviated to the letters EMF. So whenever you see those letters EMF, think that it's a potential difference. So steer away from the idea of it being a force. It's not actually a force, it's a potential difference. Probably the easiest way to think of it is that it is the force that causes motion of electrons. So electromotive, electro relating to electrons, the motive relating to motion, and the force aspect being that sort of pushing. And again, just can't stress enough, it's not actually a force here. The EMF is a potential difference. So make sure you've got that very clearly identified in your mind. EMF is a potential difference. So things like batteries can be considered to be an EMF because they provide a force that causes a motion of electrons, or any device that, or any component that allows, well, that causes electrons to flow. So this process above, as I mentioned earlier, is known as electromagnetic induction. And the reason for that is that it deals with both electricity and magnetism. And the idea of induction here is that we're causing current to flow. Now, this is only one example. What we're going to have a look at as we move forward in this unit is that it's not just about a conductor moving through a field. It can be any change in the magnetic field around a conductor, and so we're going to express that as though it's when there's relative motion between the conductor and the magnetic field. So that particular explanation that we have above is one simple way of describing electromagnetic induction. We'll start with that as our basis point, and then we'll move forward looking at other ways that the magnetic field can change, or the way that the conductor moves through that field so that a current is induced.